Okie dokie, friends. On today's show, derivatives of trig functions. You knew that we were going to have to get there. You knew that trig was going to play a part at some point. And so we begin with sine. I saw the sine when I opened up my eyes. I saw the sine. So this function is nice and smooth. Smooth functions are differentiable. What I want to know is what the value of the derivative is at any point. And so the way we're going to go after that is we're going to say, okay, at this point right here, what does it appear the slope of the tangent line is? And it turns out that that tangent line looks like it's on a 45-degree angle. That slope happens to be 1. And then I come over a little bit to where we have pi over 2, and that's flat. That slope is 0. And then I come over here to this place where we cut the axis. This is about pi, and the slope here looks like it's on a 45-degree angle the other way. That slope is -1. And then we come over here where the tangent line is flat, and we're up to 1, and then similarly, and you end up with something that looks like this, and you wonder, could it be cosine x? Could it be? And the answer is yes. We have a theorem, and the theorem says the derivative of sine x is cosine x. And we can prove it in exactly the way you would imagine. We're going to take the limit as h approaches 0 of our function at x plus h minus our function at x all over h. And then somebody has to remember the formula for the sine of the sum of two angles. Oh man, you're going to go back to chapter 1 and you're going to look that up, and you're going to find that the sine of a plus b is sine a cosine b plus cosine a sine b. And now you're thinking to yourself, I got a sine x over here and a sine x over here. Let's group them. I've got sine x times cosine h minus 1 over h. And in the middle here, I've got a cosine x just sort of sitting there, and then I've got sine h over h. So let's take everybody one piece at a time. Sine x, that's unaffected by what h is doing. This, it can be proven, goes to 0. It can be proven that that goes to 0 as h gets closer and closer to 0. Just like it can be proven that this goes to 1. Of course, we did that earlier in our course. This goes to 1. So the cosine x is unaffected. It gets multiplied by 1 as h gets closer and closer to 0. And we have cosine x just like we thought. Similarly, the derivative with respect to x of cosine x is the opposite of sine x. If you don't believe me, the slope of the tangent line here appears to be -1, but sine has a value of +1. We take the opposite of the sine of x. Well, and this enables us to do all sorts of random examples, like we're going to find f double prime if f of x is x cosine x. That's a product, x times cosine x. And since that's a product, we all know what's going to happen. The product rule is so much fun. It's 1 prime, 2 plus 2 prime, 1. And so what do you got? You've got cosine x minus sine x. But I don't want f prime, I want f double prime. Oh, really? Yep, you caught that. Nice job, folks at home. 2 prime times 1, which means that this is an x right there. That's a product. Oh, glorious. So now when I take the second derivative, the derivative of cosine x is negative sine x minus, and now I have another product. The product rule is so much fun. It's 1 prime, 2 plus 2 prime. Wow. I should just stop doing math. 1 prime, 2 as it is, leave it alone, plus 2 prime, 1. And so what do you end up with? You end up with negative x cosine x, and then you got a minus sine x and another minus sine x, like that. So as long as you actually do the product rule correctly, you can do these problems. Boy, I hardly can wait to see what's going to happen when I do the quotient rule. Oh man. Let's see. Let's find g prime of x if g of x is sine x over x squared plus 1. Looking for g prime. That's quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest you won't be scared. It's all over the bottom squared. This is calc, this is calc, this is calc. And we do not, under any circumstances, try to simplify. Most especially, we do not, under any circumstances, try to cancel those things. It is one of the most common things that students try to do. It cannot be done. Don't do it. Okay? Okay. So we should probably take a look at the others. Because while sine and cosine are the sexy trig functions, there are 4 others that are worthy of study. So when I'm looking for the derivative of tan x, that's the derivative with respect to x of sine x over cosine x, that's a quotient. I know how to take derivatives of quotients. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. And you're already thinking to yourself, wait a second. What is that? Where have I seen cosine squared x plus sine squared x before? Ah, yeah. Cosine squared x plus sine squared x is 1. And we know that 1 over cosine is secant. The derivative of tangent x is secant squared of x. In a similar way, the derivative of cotan x is the negative of cosecant squared x. But what about secant of x? What about that? Well, that's the derivative with respect to x of 1 over cosine x. So we again utilize the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest you won't be scared. It's all over the bottom squared. This is calc, this is calc, this is calc. So now what happens? Well, this is gone. And these are gone. Now this, I know what that is. That's tan x. And this, I know what that is. That's secant x. And so we say that the derivative of secant x is secant x times tan x. And in a similar way, the derivative with respect to x of cosecant x is the negative of the product cosecant x and cotangent x. It's very similar. You'll see a lot of analogies. So let's find all values of x for which the tangent to y equals sine x cosine x is horizontal on 0 to 2 pi. All values of x for which the tangent is horizontal. Well, I know what a horizontal tangent line is. In a horizontal tangent line, the slope is 0. So that's what that means. The slope is 0. And so I'm going to use the product rule. The product rule is so much fun. I hate your song, stop singing your song. And so you've got cosine squared x minus sine squared x. I want to know where that is 0. And the awesome thing about that, I want to know where y prime is 0, which means I want to know where sine squared x is cosine squared x, which means I want to know where sine squared x over cosine squared x is 1, which means I want to know where tangent x is 1 or negative 1. And that being the case, there are only 4 possible options, and they are no, they are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the 4 values of x where tangent x is either 1 or minus 1. That's your 45-degree angle on either side. So, some things for you to consider if you're looking to do some work on your own. Things you might want to consider. You might want to find f prime if f of x is 1, oh, let's do it this way, 1 plus tan x over 1 minus tan x. You may want to find what f prime is. You may want to find the tangent line to y equals x cubed plus cosine x at the point 0, 1. And you may want to say, okay, if Pete the particle is moving such that his position is 300 plus 40 sine of t, what is his velocity at pi over 3 and his acceleration at pi over 3? And those are things to think about. Hit the pause button. You work those through. Let's see if you get the answers. All right, I hope you hit the pause button. Here's f prime. F prime is bottom times derivative top minus top times derivative bottom over bottom squared. Now, it is not necessary to simplify that, but if you do, you get 2 secant x over 1 minus tan x squared. Over here, the tangent line is y equals 1, and over here, these values are 20 and negative 20 radical 3. So there you go, 13 minutes of fun and excitement. I'll see you soon. Thanks, everybody.